Introduce right away Lenore Blum from Carnegie Mellon.
Okay, so thanks, Sherry. And thanks for you all being here. Okay, I was here 2 years ago, so some of what I say will be a little bit repetition, if any of you were here. And I was here also 2 weeks ago at the ML workshop and giving another talk. So some of that also will be a little repetition, but I hope there will be some new for everybody. And I'll talk about world models and the emergence of a first-person perspective in an AI or machine. And this is joint work with Manuel and Avrim. Okay, it's this family business, the family. Okay. Okay, so here are some questions that I would like to address. What are world models? That's the topic, one of the main topics of this workshop. And what is a first-person perspective and how those two go together? And then finally, can machines have it? Okay, so that's more or less what I want to cover. Okay, so let's go to what are world models. And I'm going to go back to Kenneth Craik, who was a Scottish philosopher and a psychologist. And he wrote this book in 1943, The Nature of Explanation. And I think he has really the best sort of overall picture of world models. So that's going to be my basic definition. Now, notice this book was written in 1943, which is the same year as the McCulloch-Pitts paper comes out on neurons. So it's very interesting about this. He also sadly died very young on bicycle. He was on bicycle and a car crashed into him. And so he may not be that well known, but should be. Okay, so this is Craik's definition of world model. And he even uses the words early on. And he says, and I have some numbers here which I put in because I think they're interesting points that he's making. If the organism carries a small-scale model of external reality and its own possible actions within its head, it is able to, 1, try out various alternatives, 2, conclude which is the best of them, 3, react to future situations before they arise, 4, utilize the knowledge of past events in dealing with the present and the future, and 5, in every way to react in a much fuller, safer, and more competent manner to the emergencies which face it. So I think this is very contemporary for today, and in fact, for me, this is a very good working definition for a world model. Okay, so I would like to thank Aaron Nayebi, who actually introduced me to Craik, and really I think it's hoping that many of you will look into this too, because I think it's extremely relevant. Okay, so that's the definition the working definition for world model. So what is a first-person perspective? And now I'm going to go to Francisco Varela, who is a neuroscientist. He got his PhD with Torsten Vila at Harvard, and became Maturana was his mentor. He's a Chilean neuroscientist. He had a laboratory in Paris, and I understand that William was actually in that laboratory. Okay, so this is the 30th anniversary of his paper on neurophenomenology, and there's a conference in a few weeks, which I'm going to in Chile, to honor that. But I'm going to make some quotes from a book that he co-edited with Jonathan Shear, who I think was actually at Berkeley at one time. And what he says is, by first-person events, we mean the lived experience associated with cognitive and mental events. Sometimes terms such as phenomenal consciousness and even qualia are also used, but it is natural to speak of conscious experience or simply experience. These terms imply here that the process being studied, vision, pain, memory, imagination, etc., have a subjective side. So, of course, what he's talking about is the hard problem of consciousness, and I'm going to equate first-person perspective in this talk with the hard problem of consciousness. Okay, so many view the hard problem as needing a new kind of science to explain subjective experience, and we view the hard problem as a challenge to show that subjective consciousness surely is computational. Okay, can machines have it? Now I'm going to go back to Craig again and read what he has to say. So he says, assuming then the existence of the external world, and I put in world model, I have outlined the symbolic theory of thought in which the nervous system is viewed as a calculating machine, the same year as 43 as the McCulloch-Pitts paper, and have calculators capable of modeling or paralleling external events, and have suggested that the process of paralleling is a basic feature of thought and of explanation. The possessor of a nervous system is thus able to anticipate events instead of making invariable empirical trial. Okay, so this is his notion about the nervous system being sort of like a, he calls it a calculating machine. This is 43, that's his terminology. Okay, and I'm going to replace in what he says here the Conscious Turing Machine, which is I'm going to talk about. And this is our machine model for consciousness or first-person perspective. So assuming the existence of the external world and world model, the Conscious Turing Machine is viewed as capable of modeling or paralleling external events. The possessor of a CTM brain is thus able to anticipate events instead of making invariable empirical trial. So I'm adapting Craig again here in kind of a pre-justification of what we're doing. Okay, so can machines have it? And here are some specs for our Conscious Turing Machine. I'm not going to go through the formalism here, but we've defined it as a seven-tuple. So we're inspired in part by Alan Turing's simple yet powerful formal model of computation, the Turing machine, and Bernard Barr's global workspace theory of consciousness, often called the theater model. And so the CTM, or the Conscious Turing Machine, is our candidate for a simple, formal, theoretical computer science model of consciousness, which at a high level explains a number of features of human conscious phenomena and aligns at a high level with many of the major theories of consciousness. Okay, but before I go ahead, I want to make sure I'm clear on this. The CTM is not a standard Turing machine. What gives the CTM its feeling of consciousness is not its input-output map, nor its computing power, but what it's doing under the hood, how it's operating. And the CTM is not a standard global workspace model. It's a formal, the global workspace model is more of a metaphor. This is a formal TCS model. It has a well-defined competition for processors to get their information into short-term memory on stage, has no central executive. And its subjective feelings come from, in addition to the global workspace, from the co-evolution of brainish, which is CTM's self-generated, multimodal or multisensory internal language, so self-generated, and its model of the world. So its feelings are coming out of this. And then finally, I want to just say the CTM is not a model of the brain. It's way too simple for that. So. Okay, with all that qualification, let me go ahead and give you a little bit of the architecture before I go into the construction of brainish. Okay, so what is STM for our model is the stage. It's a broadcasting system, and it can hold one chunk of information at a time. George Miller talked about the magic number, 7 plus or minus 2. We're looking at, for simplicity, we can get away with one chunk, and so one will do for us. Okay? It's like a broadcasting stage, it's a broadcasting system. And LTM will be the audience. Well, this is a huge audience that we're assuming. We're assuming like 10 to the 7th processors, or maybe 2 to the 24th. We're looking binary for our calculations. Processors, huge. All the CTM processors are going to be included in LTM. Now, again, for simplicity, all the processes are in LTM. STM is just a broadcasting station, it's not a processor. All the other ones are in long-term memory. Okay, at t equals 0, almost all the processors are generic. They're powerful and generic, but we do have some that are built in. So we have input processors. You can think of those as sensory processors, output processors, which you can think of as motor processors, gauge processors, homeostats. You can think of like a fuel gauge. And again, all others are generic, but we build in a few. Okay, to start, again for simplicity, all the processes are unlinked to start with, and links will form as time goes on. I'll mention that in a bit. Okay, and we could have things linked to, some processes linked to start, but again for simplicity, we're going to say unlinked. We have predictive learning algorithms built into the processors. An important one that we have are Avrim Blum's sleeping expert algorithms, which help balance the weights that processors give their information that they want to get up into short-term memory onto the stage. Okay, and each processor has its own internal language, but the processors communicate in Brainish, which I said is CTM, self-generated multimodal language. And what this language does is it fuses words, like English words, images, sounds, smells, sensations. Okay, for example, Brainish label for a rose might be a fusion of the red color, the sweet smell, and the soft touch of the petal. So all fused together in a Brainish word. Okay. Okay, so now let me just quickly go to the up tree, down tree, and links. Those are important components here. So the up tree is a conduit for the competition to get into STM. And what these processes do is at every moment of time, every processor puts in a chunk into a competition. This competition is very much like a tennis match, and as the chunk wins at one level, it moves up the next level, and so forth. Okay, and in the literature, chunk is often just informally defined as a few words, maybe a sentence, a small concept, or something, but we have to formally define it, so we define it as a 4+ tuple. So it starts out with the address of the processor that put in the information, and if there are 10 to the 7th processors, that's like a 7-digit number. The time could be a 10-digit number. The gist is succinct information in Brainish. So one can think of the gist as like a frame in a dream. So if you're dreaming, you may see a picture, you see some color, some movement. You might have a fear, you might have a nightmare. So all of that particularly in the frame of a dream. So those sensations all together would be in a Brainish gist. Okay, and the weight is the valence number, it's plus or minus. It's the importance or the value of the confidence that the processor gives its gist. Okay, a couple of things, I'm not going to go into detail, but it's like a tennis match, as I said, but it's fairer. This takes the place, the competition takes the place of having a central executive deciding who's the winner, and we think a central executive is not a very good thing. It could be biased, it's not omnipotent and all that, so we feel this is a better replacement. The competition is a better replacement because it takes in can take in lots of information. It can have outlier information get into the stage and be broadcast. It can discover latent talents. Okay, so we actually think it's a good model for AGI also. Okay, as the chunk moves up the competition, the first 4 components of the chunk stay the same, but the auxiliary information, I won't go into that in detail, but it slowly gathers more and more global information. So when one gets the winner on top, we have the original information that was put in plus a lot of global information. Okay. And another thing which I won't go into, but we were determined, particularly Manuel was determined that this would be totally deterministic model But we found that to keep it deterministic, we're also looking for simplicity, parsimony, right? We're looking for simplicity. Every time we wanted to do something, it would just be so many details we had to put in. And the moment we put what we call a coin toss neuron at each of the nodes as the chunk is going up, everything became very simple. So a little bit of probability here simplified the whole model. So we do have a little bit of probability here. And in fact, the winner, this is fairer than a tennis tournament because the winner is going to win with probability proportion to its rank compared to the sum of the other ranks. So if you're playing in a tennis, whoever you play with first is going to, and so in our model, because it's just determined, the winner is determined by its probability of its weight over the sum of the other weights, the rank over the sum of the other ranks. It's independent of location. Its winning probability is independent of location, which is not true in a tennis or a chess match, because who you play with first will determine a lot of your future. Okay, so we like this algorithm. I gave it on 2 weeks ago, so you can, if you look at the thing, the talk I gave 2 weeks ago, I give it that in detail. Okay, but I'm not going to do that here. Now, the down tree is the conduit for global broadcasting. So as soon as a chunk wins, okay, it's immediately in the next tick broadcast simultaneously to all long-term memory processors. Okay, immediately goes down. And as I mentioned, so all the processors are getting a lot of information. They're getting the address of the processor that put in the winning chunk. They're getting the gist, what was put in, the information that was put in. They're getting the valence of what was put in. And as I mentioned, the auxiliary information is collecting more and more global information. So they have a sense of where everybody was to start with also. So there's more information coming in here. Okay, so built into the long-term memory processes, I have to tell you a few more things. The processes, when they get these broadcasted chunks, they store them. They store all of them. And so we call that the global brainish dictionary, and I'll tell you more about that as we go along. But all the processes have the same global brainish dictionary. They're storing all the chunks that they're not the ones that they're getting by any other process, but just the ones that are coming down through the global broadcast. And we can define a brainish word then to be a pointer to the chunk. So if they're saving all those chunks, if later on they're given the word PT, they can actually look it up in their dictionary, okay? So that's the word as the PT is the pointer to the meaning. Okay, and a brainish gist for us will be a sequence of most 8 words. We want it to be succinct, not very, very long. Okay. So we also have triggers built in. If a broadcasted chunk is absolute value of its weight, so the weight could be positive or negative, but if the absolute value of it is higher than some threshold, then all processors have to unpack to the gist. What they have to do, and we'll go into this a little bit, they have to go and find the meaning of the gist, not just look at the gist itself, but really decipher what it's really telling it, to what its meaning is. And if it's actually that, that weight is negative, okay, not that it's just the absolute value is large, but if it's negative, all processors must try to counter extreme negativity. And this will come up again very shortly. Okay, so that's built in. And then, as I mentioned, there are no links to start with, but we do have a Hebbian-like principle that processes that broadcast together link together. So that's one process that broadcasts, another one broadcasts similarly right after it, they will link together, and that's how links are formed. And so what links do is they turn slow communication that has to go through short-term memory into fast communication through long-term memory processors, or what we call the unconscious processors. So when you learn to ride a bike, you know, all of your motions you're very conscious of all of your motions, right? You have to think about all of them. But once you learn things, your motor processor is connected with your vision processor, and most everything is done automatically, unconsciously, unless, you know, a car comes to you or whatever, and we've seen accidents happen that way, right? Okay. So now finally, I want to tell you the input-output maps. So the CTM is not a brain in a vat. Okay, this is very important for us. It's not a brain in a vat. It has input maps which take information from the external world through sensors to input processors, sensory processors. Okay, and it has output processors that gives information to actuators that can affect the outside world. So there's a lot of what we call predictive dynamics going here. There are cycles of prediction, feedback, and learning in the CTM. I won't go into details, but processors make predictions. For example, when they put chunks into the competition, they get feedback, for example, from broadcasts, and then there's this learning that's happening within the processors themselves. So there is this dynamic, which we call predictive dynamics in our thing. Okay, so now I'm ready for the very first definition. I'll have two definitions of consciousness. The first one is conscious attention, okay? In the consciousness community, this is often thought of as access consciousness, but we call it conscious attention. So we say conscious attention in the CTM is the simultaneous reception by all long-term memory processors of the global broadcast of the winner. So when they all get the information of the winner, we're saying they're paying attention. They're paying conscious attention. The CTM is paying conscious attention to that broadcast. And so we have an axiom here. This is our first axiom, which I think is pretty straightforward. We say that global broadcast evokes a unitary experience. When all the processors get the same information, our axiom is that in the CTM is a unitary experience. I'm not sure if this is called the binding problem, but it's related to that in consciousness science. And we call this the global broadcast axiom, or you could call it the conscious attention axiom. And you can see even here that there's something like what's called the Libet effect, because you can see that the winning chunk was put in at time t. Okay, it took h steps. H is, in this case, if there's 2 to the 24, if it's binary tree going up, the height is 24. So t plus a, 24 plus 1. So 24 plus 1 ticks are going to be the winning chunk was put in 24 plus 1 ticks before the CTM paid conscious attention to it. So it's a little bit of what's happening that we know in the brain, that some decisions are made before we're paying conscious attention to it. Okay, so there's a delay between submission of winner and conscious attention. And the reasonableness of our definitions or axioms lie in the number of phenomena associated with consciousness that the model can exhibit easily and explain easily and naturally, and agrees at a high level with cognitive neuroscience explanations. So Libet effect, in our PNS paper, we talk about blind sight. So we look at phenomena that is usually associated with consciousness in humans, and we show how in the CTM can experience that. And the ones in our PNS paper, and one I talked about, I think 2 years ago, blind sight, inattentional blindness, change blindness, and you can look it up, or anybody wants to know about it, I'll talk to you later about that. Okay, so now we have attention, but what about this subjectiveness, this first-person subjective experience? So we're saying attention is not all you need, okay? And what we need is, I see some smiles because people know what I'm using, parable here, okay. Coevolution, what we need is the coevolution of brainish and the model of the world in the CTM. Okay, So the model of the world processor maintains models of the world and CTM in these worlds. The model of processor and its models is widely distributed, and in fact, for simplicity, we're assuming that in every processor has the model of the world processor in it. It's a useful fiction, though, to think of the model of the world processor being a single processor, but that's not the case, or the model of the world being one thing, but it's not the case. Okay. And what the model of the world processor does is it labels sketches in the model of the world with multimodal brainish gist, including labeling sketches of actuators as self when the CTM consistently detects the actuators carrying out its requests. So here's an example of a little baby who, by power of thought, is moving its left leg. And in its model of the world, it's seeing that it's labeling its left leg as self. It's trying in a while to do the right leg. It can't quite do it yet, but its left leg gets labeled self. Okay, but let me go specifically to the CTM and how this is happening in the CTM formally. Okay, how the model of the world is being created. I have 5 minutes? Okay. Okay. The newborn CTM starts out with a foggy model of the world. And let me tell you what that is. CTM's first broadcasted chunk, we'll call that the initial sketch. So some processor P0 at time 0, well, it didn't have any language, so we're going to say that just the nil word, and with some weight, got into short-term memory and got broadcast. And that very first chunk we'll call the initial sketch, okay? And sketches in general will be broadcasted chunks in our model, okay? And we'll give a name to this sketch, and that will be the first two components of the chunk. So P00 will be the name of the first sketch, and in English, think of it as blob 0, okay? Blob 0 will be the English version of brainish P00, okay? So P00 is a pointer. So if any processor ever sees that word, P00, it can look it up and know that it was really connected to the very first broadcasted chunk. Okay, that's its meaning. That's the first thing it ever knew. Okay, and brainish words, as I mentioned earlier, are such pointers. And so we have a word going to what the chunk would be the meaning. And there's something similar, I guess, in these large language models, key going to value. There's a similarity here going on, but I don't want to stress that too much. And now shortly a primal word for pain will be created, and let's see how that happens. So I don't know if you've ever witnessed birth of a baby. If you've watched this program on PBS on midwives, you see these babies being born, and the baby cries, and everybody's happy. Why is everybody happy when the baby's crying? What's going on? Okay, so let me give you our explanation of that. Okay, I told you that built in there are gauges. So we have something like an oxygen gauge. And that oxygen gauge is low, and it knows that to survive, this infant or the CTM needs oxygen or some equivalent. Okay, so it puts in a chunk into the competition with increasingly high weights until that goes above threshold. Keeps on putting in, I need oxygen, until it goes above threshold, okay? And so all the processors know they have to do something, and it's going to be a negative, okay? It's going to be a negative valence, very high negative, okay? And all processors know they need to do something to get that negative weight down, okay? But what the heck, they don't know what to do. So they just do what they do. So the motor processor is attached to these arms and legs, whatever, and they flail. If you see the baby flailing, and it pees, poos, all these things happen all at once. And then the vocal actuator screams and cries. Wow, this works. The cry opens the lungs, and the infant takes its first breath. And the oxygen gauge then can go down, okay? So that's why everybody's happy, it's breathing. Okay, So let's see what that word is. Suppose P1 is the address of the oxygen gauge, okay? And at time T1, it put in a chunk. Well, it didn't have much to say, it's just saying nil. But for the very large negative weight that got everybody working, doing something, so it went above threshold. Suppose that's one of the chunks that was above threshold that caused these processes to do something, okay? And so we will say P1 to the, it got down, all the processes see it. We'll say P1 T1 will be the brainish word for what we call in English pain one, okay? It's pointing to that chunk, P1 T1. P1 is the process, the oxygen gauge at time T1. Okay, so brainish just is a string of at most 8 brainish words. We already have 2 brainish words here, P00, P1, T1, and if you remember what they were in English, blob 0 is in pain. We can say that right away, we have a gist. Blob 0 is in pain, so you can imagine the CTM using that gist again and again if it's in situations. Okay, so brainish sketches, words, and labels continue to evolve and build on earlier ones. So when this infant becomes toddler and he names himself Big Boy Self and he has skin knee pain, that's going to be an evolved feeling of pain built on earlier pains, the labels that are given there. And here's another definition. We say that CTM unpacks a chunk, almost done, when all processors simultaneously take note of the weight and simultaneously retrieve the meanings of all words appearing in the gist. So we're saying when it unpacks a chunk, it's got to do more than just look at the chunk. It's got to look at that gist, and it has a number of words, and it's got to look at the meaning simultaneously of all those words, which it can look up because it has it. And that's what we're saying it unpacks. When it packs a chunk, it's really getting the fused meaning of all the words in the gist, okay? And we'll say conscious awareness arises in the CTM when the CTM unpacks a broadcasted chunk. We have our first axiom from before, global broadcast gives a unitary experience. Global unpacking. Now, our second axiom will say that gives a unique subjective experience. Or say when the CTM does global unpacking, a unique fusion of the subjective experience evoked by the meanings of the words in the gist is evoked. And we have this written down kind of formally. It's an axiom that's kind of inductive. It says, unpacking a chunk evokes in CTM a unique subjective experience. And we start off with the primal ones. We say with the primal unpacking. Unpacking a primal chunk evokes in CTM a unique primal subjective experience. So when it goes back to the primal pain one, it'll evoke that initial experience when it unpacks that one. And then we have an evolved part of the axiom, or the inductive part. Unpacking a chunk with evolved gist evokes in CTM a unique fusion of the subjective experience evoked by the meanings of the words in the gist. So it's a little bit more complicated, but it fits in very nicely with a lot of the literature. CTM becomes consciously, as it becomes consciously aware of more and more broadcasted chunks. The model of the world processor may call attention to this with a very high weight. And the word T pointing to the broadcasted chunk that calls attention to this becomes a word for consciously aware or simply conscious. And as CTM becomes consciously aware of more and more broadcasted chunks, the words, the model of the world will label sketches that PTM is conscious. Okay, so I won't go through a little bit more of that, but when the CTM broadcasts CTM is conscious, it itself, when it unpacks, will feel itself conscious. And this is very much like Michael Graziano's attention schema theory. And I want to just end here with a little bit of how does this fit in to there's a whole, there may be 250 theories of consciousness. Robert, Kevin Mitchell, no. So there is a website which lists 250 or 350 theories of consciousness, including ours. But I would say that about 10 of them are reasonable theories, are the major theories. And so where do we fit in? So we align with 10 of actually the major theories, about 10 of the major theories at a high level. And what's interesting, the two contentious and the two primary theories, the global workspace theory and IIT, which is integrated information theory, those are the two major theories. They're at loggerheads. And people say, well, how can you align with both of these theories? Global workspace, because we're influenced by that, but IIT, because we have hi-fi, we have a lot of integration, we have a lot of feedback, hi-fi. So how can we align with both? But in the literature, global workspace says that it's happening in the brain in the prefrontal cortex, and IIT says it's happening in the brain in the posterior cortex. Well, we're not saying it operates anywhere. We're just saying that we need that functionality, but we're not tying to any particular place in the brain. So it's not tied to any location. Okay, so that's about all I want to say. Manuel just shouted out Kevin Mitchell. He has a blog post where he gave 15 questions about what a theory of consciousness should entail. We actually went through all his questions. There are actually 15 times 3 questions, really. And if you want to look at our archive paper, we go into detail, answer all his questions with respect to the CTM also. So that's another thing. So we have predictions. I can talk to you later, and summary and conclusions, but our final conclusion is that CTM is clearly buildable, and at a higher level, it exhibits and explains phenomena associated with human consciousness. It aligns and integrates underlying principles of major theories. It addresses questions that a real theory of consciousness should encompass, and I'll finally say, AI consciousness is inevitable. Okay, conclusion.
All right, we have time for maybe one question while Robert sets up.
Yeah, okay. Any questions? Yeah.
Language-brain issue sort of evolves as we experience consciousness in the model. Is there a prediction to the complexity of this language? If, like, I'm sorry if I missed it, but if there's t-time steps, do I expect this complexity to be exponential or sort of?
Well, first of all, we're limiting to 8 words, first of all. So the words, and what we're saying right now, and I think I'm not answering your question, but I just want to say this. We're assuming for our second axiom that we're just going down one level. You don't have to go way down to the bottom because you've built up this kind of experiences inductively. So we're saying certain processors may want to go down further to find out more and more detail, and that's going to spread out, of course, but we're only requiring them to go down one. So right now, the complexity is not. We don't have a grammar for this language. We could. If you notice the way I was doing it there, I have, as in many languages like Creole or something called Tokiponan, there is the subject and the adjective afterwards. So blob, pain, that sort of thing. So that might be the right kind of grammar for this, but we haven't thought of grammar yet for the language. Yeah, okay. So.
Thank you very much.
Take my, oh yeah.
Right. It is my pleasure to introduce Robert Barton from the University of Durham, otherwise known as our one and only evolutionary biologist.